Hi everyone. My name is Amit, and I'll be talking about the Opal-RT microgrid test bench in this short presentation. But prior to getting into the Opal-RT microgrid test bench as such, I believe that it's important that we set a stage and understand what power hardware in the loop-based simulations are and what their utility is when it comes to hardware implementation and testing. In a typical workflow, wherein you would want to implement a hardware setup, or you would want to test a hardware equipment, or you would want to set up a lab for your research students in an academic setting, for instance, you would start with an idea. You would perform some simulations to validate whether a particular concept that you would want to implement in hardware works or not. You would then go about doing design specific simulations and eventually with hardware implementation and testing. With such a methodology or a workflow, what often happens is that there is a situation where you might have to modify your simulations, modify design specific simulations. Let's assume that you are building a PV inverter and perhaps the protection scheme that you have implemented is not working as it should in hardware, which means that you might have to go back to your simulations and modify it. In certain cases, perhaps the idea of what was being developed is itself something that needs to be reworked on, which means you might have to go back 2 steps and start off with doing some more validations prior to going back to hardware implementation. What essentially happens with such a workflow is that there is a rework wherein you would want to go back, modify your simulations, redevelop your hardware, perform testing again, and so on. And this kind of back and forth can consume a lot of time, and you would end up wasting time and money with this approach. What can be an alternative as a solution to this is to essentially have stages midway between having your simulation, wherein you do simulations for design specifics and you have a final hardware implementation of, let's say, a research lab for your academic laboratory, or it could be a product that you are designing in an industry. But instead of going from simulations to hardware implementation directly, we can have stages midway where you either do testing with scaled down power prototypes or you perform power hardware in the loop simulations. The goal here is essentially to compartmentalize hardware implementation. The idea is that you do not want to go to hardware implementation directly, but rather you would want to go to hardware implementation in steps. You might probably be able to implement scaled down prototypes in certain cases. You might probably be able to perform power hardware in the loop simulations in certain cases, and so on. And this would mean that even if there is a necessity to go back and forth with going back to the simulations, you do not go back after coming to the final stage, but rather you identify bugs, identify problems, identify issues with your final hardware implementation midway in the process. And this can save both time and money. So essentially, that is what is important to understand here. And the fact is, with power hardware in the loop simulations, and this the advantages are essentially true for both academic in an academic setting and in the industry. And by being able to compartmentalize hardware implementation, there is a significant amount of saving in both time and money. To understand now what power hardware in the loop simulations are and how can we introduce it in our process of, let's say, developing a hardware equipment, setting up a research lab, and so on, let's consider a particular application use case of a traditional approach to a device under test or a unit under test validation. Let's say in your lab, you are developing a microgrid. It consists of a wind turbine system, it consists of a PV inverter system, and so on. And you would want to validate whether this microgrid that you have developed in your research lab or in an industry operates as it should or not. It perhaps has a microgrid controller. It has controllers for the individual devices under test and so on. Typically, when you would want to test this equipment, you would eventually connect it to the grid because you would want to see if maybe your MPPT algorithm, if it's working as it should. You would want to verify if your wind turbine, let's say the microgrid controller, which essentially shares power between the two resources when it comes to grid integration, works as it should, and so on. So you would have to develop your hardware. Eventually, you connect it to the grid and perform your testing. Now, such a direct interconnection could be risky, particularly if the equipment that is built might have some bugs or might have some issues in its development, either in the control side or in the power side. And these bugs can lead to equipment damage of the UUT, which could be costly. And in certain cases, especially in an academic lab setting where students are operating such equipment, if they interconnect it to a grid directly, there could be a safety concern for the operator as well. Furthermore, with such a system of testing, perhaps in your control algorithm that you have developed for your PV inverter, which you want to develop in hardware, you have schemes that would be initiated if there are grid unbalances. Now, when you are connected to a real grid, an unbalance being present is not something that you can control because it could happen, but you do not control when an unbalance happens. You do not control when a fault in a grid happens, and so on. So essentially, there is an inability to perform comprehensive tests, which means that the hardware equipment that you have developed and you are testing might operate for certain conditions, but in certain abnormal conditions, perhaps it doesn't operate as it should. The solution to this is to perform power hardware in the loop-based design and testing. The idea is with a model of the simulated grid with the same application example case as the previous slide, you have a grid, you have a microgrid that you would want to test with a PV inverter, wind turbine, and several other equipment. But instead of connecting this equipment to a real grid, you rather connect it with the help of a power amplifier and a real-time simulator to an emulated grid. Now, the unit under test, which is what you are testing, a microgrid lab, which you have developed in your academic research lab, for instance, is not able to differentiate between whether it's connected to a real grid or whether it's connected to an emulated grid, because the power amplifier outputs voltages representative of the grid that is modeled inside the real-time simulator. So you model a grid in a real-time simulator, the voltages are sent through signal quantities to a power amplifier. The power amplifier outputs the required voltages across the unit that is being tested. With power hardware in the loop-based simulations, you essentially are able to perform your tests in a controlled manner. In the previous case where you were connecting this equipment to the grid, if there is a maloperation of the equipment that is being tested or the equipment that is being run in hardware, there might be a large amount of current that can be drawn from the grid, which could damage equipment. But with such a setup, with the power amplifier, which has its own protection scheme, which has its own power limitation, and so on, the tests that are performed can be controlled. Furthermore, with a power amplifier setup such as this, as I mentioned earlier, with a real grid, perhaps there are some conditions for which you are not able to test your equipment, and therefore there can be chance of equipment damage if such a scenario exists, such as an unbalance, for instance. But with a setup such as this, you can model unbalance, you can model faults, you can model situations which can occur in real life scenario, but emulate it in adequate detail such that you can test your equipment to be ready and used for several real life scenarios that can exist. PHIL simulations essentially allow you to compartmentalize your hardware implementation, and the main advantage is that it allows rework and design rework that can exist if you are directly connecting to a grid, and there can be issues of real fault situations which might make your equipment not operate as it is intended to operate. The real-time simulator and the power amplifier together is what is constituted on the Opal-RT microgrid test bench, which is what I'll be talking in the next slide. The Opal-RT microgrid test bench with a part number of OP1420 is a complete integrated high-fidelity power hardware in the loop test bench. As I explained in the earlier slide, a power hardware in the loop simulation is possible if you have a real-time simulator, which is shown here as an OP4512, which is where your simulation model runs, and you have a power amplifier, which essentially translates simulation model behavior to real voltages, which can be connected to an external equipment. The integrated OP1420 test bench, in addition to the simulator and the power amplifier, which essentially allow the possibility of power hardware in the loop simulation, also has additional components such as the OP1460, which is a microgrid bus bar, which allows you to connect multiple hardware equipment that you would want to test to the terminals that are shown here in the schematic. Furthermore, you also have monitoring panels such as a power amplifier panel, which is shown here, which measures real current and real power flow from a real hardware test equipment that you would want to connect to a power amplifier system and test it out. The main advantage of an integrated test bench such as this is that the simulation environment and the power amplifier environment are both provided by Opal-RT, which means that the test bench in itself is completely compatible and integrated together. The user will not need to worry about identifying the right library components, identifying the right cables, making sure that the interfacing between them works as it should, and so on, because the product that is provided by Opal-RT in the form of a 1420 test bench is a completely integrated test bench. The heart of the system essentially consists of the power amplifier, which is what translates simulation behavior to real voltages and real currents. The bandwidth of the power amplifier that we have can achieve bandwidths up to 10 kilohertz, which means that you would be able to emulate switching behavior at a considerably high harmonic content. You would be able to emulate several transient conditions within this bandwidth as well. The THD of the power amplifier is less than 0.75%, which means that you have a high fidelity emulation that is possible, and the emulated grid from a system such as this, or an emulated wind turbine from a system such as this, is close to a real grid or a real wind turbine. The latency of this system is less than 10 microseconds, and the fact that we have a low latency is what ensures that we are able to achieve a high bandwidth. The system can operate both in current and voltage mode operation, and this is important because depending on the equipment that you would want to emulate, if it's a grid, you would want to do voltage mode operation, or if it's a PV inverter system or a wind turbine system, you might need to do current mode emulation, and both these modes of emulation are possible. We have unconstrained 4-quadrant operation, which essentially means that if you procure a 5 kilowatt power amplification unit in the form of an OP-1420 test bench, you would be able to do 5 kilowatt of sourcing and 5 kilowatt of sinking, which is unconstrained 4-quadrant operation. The standard configuration of the equipment that we have with 1420 is up to 3 amplification units of 5 kilowatt each. One amplification unit is capable of achieving either 208 volt line-to-line 3-phase or minus 400 to plus 400 voltage of DC, and each amplification unit is 5 kilowatt of power. Now, non-standard units can be tailored upon request. For instance, our European customers use our OP-1420 test bench for 400 volt line-to-line 3-phase applications, and this is perfectly possible. And based on your requirements, we can have non-standard units that can be developed as per request. An important component in the test bench, which I briefly touched upon in the previous slide, is the OP-1460 bus bar. And with this, we can essentially see how we can go about compartmentalizing hardware implementation. Let's assume that you have a large microgrid which consists of multiple hardware equipment. You can either have all hardware equipment that are available in real hardware and test it to an emulated grid. On the other hand, you could also have, let's say, an emulated grid and an emulated wind turbine, for instance, also developed with the help of a power amplifier, and you can go about testing only your PV inverter, which is available in hardware. With the 1460 unit that is present in the OP-1420 cabinet, you are essentially capable of connecting up to 3 hardware equipment which you would want to test, and you can emulate either a grid or another DER that you would want to test with the system. So an important advantage is also seamless integration with the simulation environment, which I said is an important requirement for users because you do not want to spend a lot of time developing units or developing components, so that you can have libraries of interfacing and ancillary components that you would want to develop to be able to perform your research. But with an integrated test bench such as OP-1420, you have library components which are provided to users. You also have a microgrid model which is provided to users with an OP-1420, so that it allows users to have a kickstart and directly start with their research work, either modifying the microgrid model that is provided to them as per their requirement, or developing a model from scratch. Essentially, any model that can be developed on the Opal-RT real-time simulator can be emulated with the help of the power amplifier, which is present in the OP-1420 test bench. I hope this gives a quick overview of the OP-1420 test bench and what essentially are power hardware in the loop simulations. But in the earlier slide, I also talked about another alternative to be able to compartmentalize hardware implementation, and this is essentially doing a compartmentalized hardware implementation with the help of downscaled power prototypes. Now, with downscale power prototypes, the idea is that, let's say we have a research lab setting and you would want your students to understand how a microgrid operates. Now, be it at 5 kilowatt or be it at 500 watt, the aspects of control interaction, the aspects of control of individual DERs and so on a bigger picture operate in a similar manner. So therefore, being able to develop a downscale prototype means that you would be capable of having a lab setting which can be used for academic research, especially if the focus of research is the control development and so on. The main advantage of a downscale prototype such as this is safe and comprehensive tests with a reduced chance of equipment damage, and you are essentially able to understand actual utility behavior at downscale power levels. The downscale prototype is essentially the Bitlismen Power Lab ecosystem trainer kit, which will be talked about by my colleague Gebor next. Wallace, would you want to transfer it to Gebor?
Yeah, sure. So thank you very much, Amit, for the presentation. It was very interesting. It was a very good overview also about the MICROGRID PLE test bench. So thank you for that. And now we'll move to our next presenter, which is Gevord from Bitlismen. So Gevord, I'm giving you the control, and then you can start your presentation.
Thank you all, and greetings to everyone. So I would like firstly to thank Opal-RT for organizing this webinar and all the attendees for having time for participating. Bitlismen is established in 2004, and since we design and manufacture a wide range of energy-related trainers for academic and teaching, and also research. And I'd like to introduce our PowerLabs ecosystem, which is a product family of energy trainers. The ecosystem includes trainers for renewable and conventional energy sources, power transmission, power distribution, power protection, smart grid, etc. All the trainers within the ecosystem are compatible to each other in terms of the voltage levels. And besides using them as standalone trainers, they can be also connected together to form different microgrids and smart grids. We highly value the students' full involvement in the experiments. This is why we take care of all the safety measures so that the students can implement the experiments by themselves, starting from the interconnections of the modules to the very end of the experiment. And even if they do any mistakes during these connections, it won't hurt them and won't cause any damage to the equipment. We highly believe that the trainer should provide as much as possible the same experience as the students would have on a real field. This is why in our trainers we use real industrial hardware components like real wind turbines, PV panels, water turbines, etc. We also emulate the environment which the trainers operate in. For example, we emulate the real wind for the wind trainer, or we use the halogen lamps to emulate the sunlight for the PV system, etc. This environment emulation also makes the students connected to the topic and makes it more interesting, realistic, and deductive. Our trainers come with the software, and the trainers are equipped with a control and measurement module that implements all the real-time power measurement and analysis, including voltage and current oscillograms and harmonic analysis. As for the curriculum, we provide very comprehensive manuals that include not only the steps of the experiments, but also theoretical information related to each experiment. The PowerLabs ecosystem trainers also integrate future technologies to enhance their capabilities. Particularly, we integrate augmented reality with digital twins of trainers that are connected to the real hardware in real time. We integrate also artificial intelligence, where we provide an API for the users to build their AI models and train them for different algorithms. The other technology is industrial IoT, where we allow the users to transmit their data to the IoT dashboards, and they are able to create their dashboards and use the data transfer using the different IoT gateways. And of course, the last technology, we called it mixed power microgrid, which is the topic that we are discussing today. And as the name explains itself, it is a mixture of real environment and the digital power hardware in the loop simulation. In this simple diagram, in the simple diagram, I try to explain how the real hardware can interact with a digitally simulated agile system. And this revolutionary approach allows to have real power connection, meaning the real power flow from real world to the digital simulation and vice versa. For demonstrating it to you, Opal-RT and Bitlismen have prepared the following setup, which is a small microgrid that contains parts that are implemented physically, and there are parts that are digitally simulated. And we have prepared a video which demonstrates the setup in the more detailed way. So let's watch it together.
Hello, my name is Georg. I'm a systems engineer at Bitlismen. Today I'm going to demonstrate our joint solution with Opal-RT for a mixed power microgrid systems. This revolutionary approach allows to interconnect real physical hardware with PHIL simulation and enhance the research capabilities in the energy sector. In addition, this approach makes the PHIL accessible for undergraduate and postgraduate students. In this setup, I will demonstrate how the real power flows from the HL simulated digital microgrid to the physical microgrid and vice versa. Now let's see what the system consists of. Here we have a small microgrid setup that includes indoor solar power generation source, outdoor solar power generation source, power transmission line with step-up and step-down transformers, distribution substation with a double busbar, physical loads, other components to form a microgrid, Opal-RT bench consisting of OP4510 real-time simulator and OP8110 4-quadrant amplifier, and a SCADA software that monitors and controls the entire system. So we have three different renewable energy sources. The indoor PV system works in off-grid mode and through the physical power transmission supplies the simulated RLC load implemented in Opal-RT simulator. The outdoor PV system works in on-grid mode and is synchronized to the mains grid via grid tie inverter. The simulated wind generation source that is implemented in Opal-RT simulator has two branches. One of the branches supplies the physical load on the output of the physical distribution substation, and the second one supplies another physical load on the output of the manual transfer switch. In this setup, all the items that are inside dotted rectangulars are physical components, and the ones that are inside the cloud are digitally simulated. I have already implemented all the physical connections, so let's run the system. Now when the system is running, let's see what we have inside the SCADA software. In the home screen, we have a whole single line diagram of our system. Here we can monitor the statuses of the switchgears and some measurement data. On the second tab, we can control the physical switchgears, transformers, bus bars, and also sunlight of the indoor PV system. On the next tabs, we have the real-time power measurement data like waveforms, RMS values, frequencies, harmonic analysis, etc. There are two options to run simulated models. The RTLab software that allows to run the Simulink models on the Opal-RT simulator, and another option is the test drive software that allows to run the Simulink models and monitor and control the model from the LabVIEW panel. Here we also have a single line diagram of the simulated parts, control over the simulated switchgears, RLC loads and wind speed, and the power measurement data. Let's run the Opal-RT simulator and try out several things. Now on the test drive software, we will connect the switchgears of DER2 and DER3. Okay, and now we can go back to the SCADA software. Now I will connect the manual transfer switch, which will connect the load to the DER3, and also the bus one of the bus bar. Here on the next hubs, we can see the voltages generated by the simulated wind model and the real current flow that flows from the digital grid to the real physical loads. Here we can see the RMS values of the electrical parameters, the frequency generated by the wind turbine. We also have the power analysis, including the active power, reactive power, and apparent power. We have the power factor and harmonic analysis, which includes the total harmonic distortions for the voltages and currents and harmonic spectrum, up to 64th harmonics. Now we will turn on the indoor PV system, which will supply the simulated RLC load. For that, I will specify a certain sunlight. And here we can go to the test drive software and manipulate with the simulated load parameters. Here we can change the resistance. We can turn on inductors and capacitance. Now let's specify resistance value, and we can go back to the SCADA software. So here we can see the voltage generated by the PV system and the current consumed by the simulated load. We can also turn on inductor, and we can change again the resistance value. Here on the RMS graph, we can see how was the current change when we were manipulating with the load parameters. Hope you enjoyed the video. Don't forget to subscribe to our YouTube channel and check other videos. Thanks for watching and stay tuned.
So I hope that with this presentation, we could give you an overview of both power hardware and the loop-based simulations with the help of the Opal-RT microgrid test bench, low-scale power testing with the help of Bitlismen Power Lab ecosystem trainer, and so on. But essentially, the objective of this presentation is that we wanted to showcase that with a conventional approach of developing a hardware test bench or a conventional approach of developing a microgrid setup in your laboratory and so on might lead to iterative steps which can go back and forth between simulations to hardware implementation, and this can take a lot of time. And also there is a chance of equipment damage that could occur, safety concerns for the operator, especially if there are students operating such a setup. Maybe there is a safety concern that the researcher or the professor needs to take into consideration. We presented two alternatives which essentially talk about compartmentalizing hardware implementation. The first one being the Opal-RT microgrid test bench, which allows users to do power hardware in the loop simulations, and this allows you to do a more comprehensive test of your equipment or the setup that has been developed in hardware. The alternate route would be with Bitlismen's Power Lab ecosystem trainer, which allows you to do a downscale prototype test. And it was shown in the video that it gives you a SCADA overview where an operator can essentially understand how a microgrid operates, can understand how to transfer between different control modes, can understand an overview of a microgrid system and a control of the individual DERs that are implemented within it. The combined offering, which was also presented in the video with Opal-RT based power amplifier, which was essentially emulating a grid, and the Bitlismen Power Lab ecosystem trainer, which was essentially implementing a low-scale power lab setup, was clearly a next-generation research lab setup for a microgrid application requirement, which can address multiple areas of either testing at low-scale power, emulating grid conditions, emulating different fault scenarios, and so on. And it can be seen that we believe that you see it to be a good research tool that can be used for applications such as this. So that essentially concludes our presentation from my side at least, and I hope that we were able to give you an overview of the topics that we wanted to explain, and perhaps it gives you some ideas as to how you would want to implement something similar in your research labs too for your specific research application requirements.
That's great. Thank you, Amit. So thank you again for all of you who have attended the webinar. Thank you, Gavor, Dashat, and Amit for being here with us, and I hope you have learned and enjoy it. So to learn more about our upcoming webinars, you can access our webpage, oprt.com/learning journey, as you can see here in your screen. And there you'll also find several on-demand presentations that you can access at any time. And after the webinar, as it was said by Amit and Ashat, we'll send you the recording to all people who registered in our webinars. And don't forget to answer our survey when you close the webinar, because this will be important for us to improve for future webinars. So thank you again for all of you, and have a good day.